Section 7.6 is on similarity transformations. Recall that a transformation is an operation that maps the original figure, called the pre-image, onto a new figure, called the image. We dealt with this back in Chapter 4, and when we did that, we talked about congruence transformations. So when we started with the pre-image and then transformed it into the image, it didn't change size or shape. The pre-image and the image were congruent to each other. So remember, we did reflections, which were basically flips. We did translations, which were slides, so we moved the image from one position to another. And then we did rotations, which were turned, so we rotated the image. But in all three of those cases, the original figure, the pre-image, did not change its shape when it became the image. It only changed its position. Now in this section we're going to talk about a similarity transformation that's called a dilation. And that may sound familiar if you've ever been to the eye doctor and he's put drops in your eyes to dilate your pupil so that he can see your retina in the back of your eye. It's kind of the same idea. A dilation is a transformation that enlarges or reduces the original figure proportionally. Because the image and the pre-image are proportional to each other, this is a similarity transformation, not a congruence transformation. So when we dilate the pre-image and get the image, it's going to have exactly the same shape, but it's going to have a different size. It's either going to be larger or smaller than the original pre-image. A dilation is performed with respect to a fixed point, which is called the center of dilation. And a dilation also has a scale factor, and we use the letter K, that describes the dilation. If the scale factor, if K is greater than 1, then the image is an enlargement. If K is a number that's between 0 and 1, greater than 0 and less than 1, in other words, a fraction between 0 and 1, then the image is a reduction. Here's a nice little chart from your textbook, and actually there was a typo in here which I changed in red. So, a dilation with a scale factor greater than 1 produces an enlargement or an image that is larger than the original figure. So, if K is greater than 1, the dilation is an enlargement. So we started with triangle FGH, and it has a scale factor of 3 to 1 because RST has been an enlargement. So our scale factor is 3. We're not actually going to take the time to draw these. We're just going to kind of recognize what they are. But in this case, C would be the center of dilation. And what they would say is that the distance from C to F, compare that to the distance from C to R is 3 times longer than C to F. We're not going to worry about that. We're just going to focus on the fact that RST is 3 times as large as FGH. Since it's an enlargement, the scale factor K is greater than 1. A dilation with a scale factor between 0 and 1 produces a reduction, an image that is smaller. So, if the scale factor is between 0 and 1, if it's a fraction between 0 and 1, then it's a reduction. So we started with the original quadrilateral ABCD, and it was reduced basically by 1/4 to get quadrilateral WXYZ. If you're curious, the center of dilation is point C, and the distance from D to C is 4 times as long as the distance from Z to C, but we're not going to worry too much about that. The main thing to know is if the scale factor is greater than 1, it's an enlargement. If the scale factor is a fraction between 0 and 1, it's a reduction. So let's take a look at a couple examples from the textbook. Determine whether the dilation from A to B, so from blue to green, is an enlargement or a reduction, then find the scale factor. Okay, so for the first one here, we're going from A to B. Obviously that's an enlargement because B is bigger than A. Okay, so that means K has to be greater than 1. Now how are we going to figure that out? So I'm going to pick 2 sides and compare them. So in AB, and I'm not going to pick the diagonal sides because I can't count that, and I really don't want to use the distance formula unless I have to. So I'm going to use this side of A, which I can just count the boxes. So that's 4 units long. And the corresponding side of B, which is 5 units long. So I could write two different proportions. I could write 4 over 5, or I could write 5 over 4, okay? And both of those represent the scale factor, but I need the one that's going to give me an enlargement. So I need to say 5 over 4, because that is greater than 1. Since this is an enlargement, the scale factor has to be greater than 1. Let's look at the second example here. So from A to B, from blue to green, it's a reduction because B is smaller. And remember, for this, K is going to have to be a number that's between 0 and 1. So it's going to have to be a number less than, positive number less than 1. So again, let's compare some corresponding sides. I could do, let's go ahead and do the bottom here. So this is 1 unit, and this is 3 units. So I could write, using those two numbers, I could write two fractions. I could either say 1 over 3, or I could say 3 over 1. But since this has to be a reduction, K has to be between 0 and 1, and 1/3 is less. In fact, I'm just going to cross those out so you don't get confused. So this is a reduction with a scale factor of 1/3. And our last, yes, this is our last example here, says to graph the original figure and its dilated image, and then verify that it is a similarity transformation. So let's go ahead and graph triangle ABC. So -6, -3, 6, -3, 2, 4, 6, -3, and -6, 6. Okay, so there's A, B, and C. Not that one. Okay, and let's graph triangle DEF. I'll do that one in purple. -2, -1, 2, -1, and -2, +2. And that's DEF. And we need to confirm, verify that this is a similarity transformation, that this is indeed a dilation. So we go from a larger triangle to a smaller triangle, that this is a reduction, and that the two triangles are similar to each other. So what I need to show is that corresponding sides are proportional. Is AB over DE equal to BC over EF? And is that equal to AC over DF? Okay, so some of these are going to be pretty easy. I can just count some of these. So AB is 12 units. DE is 4 units. BC, I'll come back to that one later. AC is 9 units. And DF is 3 units. Now, to get BC, which looks like it's the hypotenuse of this right triangle, and EF, I can't count. I'm going to have to use the distance formula. So grab your calculator, punch those coordinates for BC into your calculator, and then EF, and when you do that, you'll get that BC is 15 and EF is 5. And so are all of those fractions equal to each other? That's 3, that's 3, and that's 3. So yes, indeed it is a similarity transformation. Add that to the bottom here. Yes, triangle ABC is similar to triangle DEF by the SSS similarity. So when it asks you to verify that it's a similarity transformation, for the most part for this you're going to be using SSS and either count if they're horizontal and vertical lines on the coordinate plane, or use the distance formula if they are slanty lines.